Okay, so today we will talk about OS 212.2D and 212.3a. And 212.2D is about the deadlock. So when we look at the first question is that this is the intersection. So first one is show that four necessary conditions for deadlock hold in this traffic jam. So you can say in this intersection.
Sorry. Where can I find the document?
Huh?
Where can I find this document?
Like a discussion board. Okay. So if you want to find this document, you can go to discussion board. So go to any other link. Go to university and go to my uni. And OS operation system discussion, and you can find in the useful tutorial website and this link. I will publish like a reference on this board, so you can go to here and look at the problem and my solutions. Okay? Yeah. Okay, so let's begin. So on this intersections, so the car are in traffic jam. So first one is show four necessary conditions for the deadlock hold in this traffic jam. So first one is mutex execution. So this means only one car on the section of the street. And hold and wait. That means a car is occupied street and waiting to move to the next section. And non-promptive. A car cannot be promptive when the car on this road. And the circular wait is a car must wait for the next car in front of it to move. So let's look at this graph. For example, the first is mutex execution is that only one car can occupy this, can go through this one. So if car A occupies this transaction, then car B cannot pass this. It must wait for car A pass this. And hold and wait. So car B must wait car A pass this section, then car B can pass this section. And non-promptive is that if car A, car B wait in this street, and if you have a new car C arrive this row, car C cannot in front of car B, so they must pass this rule, this road in order. And the circular wait is that each car must wait. So car C must wait car B finish this intersection, then car C can move. And question B is that show how to avoid this deadlock in this system. So to avoid this deadlock, you should break these conditions. So for example, there are many ways to break this condition. First, you can every intersection only allow the one direction to move. For example, in this section, you only allow every car can move to right side. That is one way to solve it. And in the other way, you can think in the real world, there are two-way, two-direction rule. So you can use traffic light to solve it, to avoid the deadlock. Any problem? So is that you can put a traffic light on here, and at one time you only allow the one direction to move. So that can avoid this deadlock. Okay, so question 2 is that consider there are they have 4 resources and 3 processes, and each process needs at most 2 resources. So show that the system is deadlock free. So you have 3 processes, P1, P2, and P3, and they need each one need at most 2 resources. So 2 resources at most. And now you have 4 resources. So in the worst case, for example, everyone already have 1 resources, and then you will left 1 resources, and you can use this 1 resources put in the any process. So for example, you put it in the P1, then P1 it can finish because it have enough resources, and then it will release the 2 resources, and then you can finish the P2 and P3. So in the worst case, it can finish. So this system is deadlock free. So, and the next question is that show that extend to general case of M resources and N process. So you must fulfill that M is greater than N, or greater or equal to N plus 1. This is the condition, because in this in the worst case, every process have 1 resources already, then it can finish. Oh, okay. Any questions here? Because so let's move to question 3. So we will introduce the Banker algorithm. For Banker algorithm, we have three metrics. One is the allocated matrix, one is the maximal matrix, and one is the need matrix. So we have 5%, P1, P2, P3, P4, and P5. And we have 4 types of resources. So A, B, C, D. You can just think A is the CPU, B is the memory, C is the GPU, D is the disk. So available A, B, C, D. Okay, so and in this one, P1 is already occupied the resources 1C and 2D, which means is 2 resources of D, and okay, process 0, process 1, and process 2, process 3, process 4. Process 0 already allocate 1 resources C and 2 resources D, and the maximal need 1 resources C and 2 resources D, and process B already have the 1 resources A, and they need 1B, 1A, 7B, and 5C, and 0D, and process 2 is the same. Two, and P4 need 4, and 0, 6, 5, 6. Okay. So we should calculate the need matrix A, B, C, D. Okay, for process 0, because it already have 1C and 2D, and maximal it will have 1C and 2D. So all resources he need 0. And for the process 1, he already have 1A, but he still need 7B and 5C. So the need matrix should be 7B and 5C. And for process 2, is that the max manners allocation. So it's he need 1A and 0B, because 3 minus 3 is 0, and 5 minus 5 is 0, and 6 minus 4 is 2. So he need 2 key resources, and P3 is the same. He only need 2C. So he need 2C, and process 4 need 6B, 6 of B, and 4C, and 2D. Okay, so this is the needed matrix. because he already have these resources, and he must need these resources. So he need these resources, and right now you have these resources free. So, and the question 2 is that is this system is the safe? Okay, so E equals max minus allocation. Two is that is this system is safe, so you need available free resources. Okay, so this may be we just A, B, C, D, and now we have free resources. And first we should look at the P0, and because P0 is the needed is all 0, so P0 can finish. Then it can release some resources. So it will release the 1C and 2D. And then we will look at the P1, because we don't have enough resources to run P1, so we will skip it. And then we will look at P2. P2 is need 1A and 2D. Then we can run it because after P0 we already have 2D resources free, so we can run P2. So then it will release the some resources. So P2 will release the 1. This is P0. P2 will release the 1A, 3B, and 5C, and 4D. And now you have 2A, 8B, and 8C, and 6D. And then you can run P3, because P3 only needs 2C, so you can run P3, and it will release the 6B and 3C and 2D. And then you can run P4, and P4 is because after run P3 you have these resources, so of course you can run P4. So you can run P4, then it will release the 1C and 4D. And then you will come back to run P1 because you have enough resources. You have then you can run P1 because you already have enough resources on B. So then if you can run every process, then this system is free. Safe.
Yeah, sorry, I'm missing some step. Can you repeat P3, the step of the P3?
P3?
Yeah.
P3 need 2C. Then we already have 2C resources, so then we can run P3.
I couldn't catch that either. I mean, why was P1 run after, like, at the end? What's the reason?
Okay, so we should on back algorithm we should repeat it again until we cannot change the scale. So we should repeat run it again.
Yeah.
It's a loop.
Yeah, you can check every step, every process. If the process resource is fulfilled, then you go to the next step and release the previous process resource.
Right. Okay.
So yeah, when you go to from P0 to P4, so you look for P0 to P4, then after you return back,
You
check
return back
which
to
process
P1.
is not finished yet. So we allocate the resource to that process.
And my question was, why was P1 run at the end? Like, what was the reason for that?
Because when you first loop, you can say you cannot run P1 after P0 because you don't have enough resources until P2 release its resources and P3 release its resources. Then you have enough resources to run P1.
Oh,
Okay. Because like P1, P2, if we do not finish, it will occupy some resources, which can run P1. Okay, any questions? Okay, question 3 is that if the request from P1 is need more resources, so which means P1 need more resources. So you should change the maximum matrix because it need more resources. So it need 4 more resources. So you delete 7 and it become 11 and
It's a request, not maximum. I think it's located with plus 4 and 2. It's a request, not a maximum. The maximum is the same, I think.
but if one X need a new request. For example, they create a new vector. You can imagine if you are coding a C++ and you create a new vector, then it will need more memory. So if this request is permit.
In the slide set, the request already include. And the request, you can see a request. That means that it's like for the location, it's not for the maximum.
Yeah, you can say P4.
Yeah, it's not. You can see the definition of request. Request vector for processing. One K instance for the resource. I think it's like it's not maximum.
So I think
is available
this is means you have a new request from the process one.
No, but they say that available is available, request the request, and location is location plus the request. Need is need minus request. It's not the maximum plus the request.
Yeah, so yeah, a little bit confused here. I also.
This is the what we say the request.
Okay. So are we talking about the request is equal to the lead?
Yes, you can like
Yeah, this is the slide. The request is from the is available minus the.
but however, in this if you have P1, you cannot manage the allocation with
No, the location is plus the request.
yes.
The
But
location
how to manage the request because
available, you have to.
for allocation is you manage 0 minus 4. You
No,
means this
allocation
one.
is plus. Allocation is plus. Allocation I is plus request and equal to new allocation. So is that the allocation P1 is 1 plus 4 and 4B and then 2C.
You can just think is you manage
You can continue, but I think this
So-
this is not reasonable and it's not make sense because the slide is said like this. If I follow yours, I think it's not correct.
okay, yeah. So maybe we can discuss later, okay? So for example, if you have a new request, then you maximum have like 11B and 7C and then the needed matrix will become because you become 11B and 7C. Then you will do bank algorithm again. And we will not change until the end. So at the end, we can, because we run P1 and it will release these resources, and run P2, it will release these resources. On P3, it will release these resources, and run P4, it will release these resources. So then we will find that if at the end we have the enough resources to run P1. So for resources A we have 2, and for resources B we have like 40, and for resources C we have like 12, and for resources D we have 12. So for needed like a matrix, we have enough resources. Then we can run P1. So this system is still safe. Okay.
I have a question.
Yeah.
So it's saying P1 arrived with a request for 0420.
Yeah.
Does that mean that it's already got like a different allocated resources already, or
You can think the process 1 need more like resources.
yeah?
So which means the maximal matrix is changed. Yeah, because they need more resources.
Oh, so it updates the maximum.
Yeah.
Okay, yeah.
so for the question 4, suppose you have called deadlock avoid, and then you define the new vector waiting, and waiting is the resources process I is waiting for. So can you redefine the max is equal to waiting plus allocation? Okay. So you can think the waiting this vector is the needed matrix. Because you just change the matrix to the linked list. You can think this waiting vector is a linked list, and this need is the matrix. So is the same to the needed matrix. Okay, so we will move to the tutorial 2A. Okay, so in this tutorial, we will look at the page replacement. Okay, you have some process, and each process have different memory requests. So process 1 need this memory, and process 2 need 400 memory, and process 3 need about 100 memory, and the process 4 need 400 memory. Okay, for the first phase is that you found the first memory which is big enough. So for the first phase, we search this memory in order. So first we search process 1 and found this location is big enough. Then we put process 1 in this location, and then it will remain 500 minus its size. So it will become about 300 size. And for the process 2, then we search this memory in order. Then we found this one can put process 2, and it will left 183 this side, and then we have we will look for the process 3 and the process 3, and we can put the process 3 on here. So, and it will remain minus 1, 1, 2. It will become which is about 1,000, 100. And then we will look at the process 4. And because process 4 is above 4,000, then you cannot put any. You cannot put it on any hole, so you cannot put the process 4 on this memory. So this is the first phase. And then you will have the best fit. Best fit means you allocate the smallest hole that's the big, which is the big enough. Okay, so which means when we look at P1, we will not put it on 5,500. We will put it on the 300. So we will put P1 on here because we will put it as small as possible. So we will put P1 on here. It will remain 18.8. And then we will put P2, and we will put P2 on 500. So it will remain 83. And then we will put P3 on here, 200. So we will put P3 on here. And then in this plan, then we can put P4 because we can put P4 on here. So every process is suitable allocated to the memory on the best fit. And on the worst case fit is that we will allocate the largest hole to this process. So, okay, so when we look at P1, the largest hole is 6,000. So we will put P1 on here, and it will remain 388. And then we will put P2 on the largest hole. The largest hole is 500. So we will put P2 on here, and it will remain 83. And then we will put P3 on the largest hole. The largest hole is this one. So we will put P3 on here, and it will remain some memory. However, when we put on the P4, there are no hole big enough to put P4. So in this plan is also not good. Okay, any problem in here?
Where is P4? Which area you put the P4?
P4, you cannot put on the west face.
Okay, so
Yeah.
it's not enough space.
Yeah, it's not enough space, so you cannot put in any.
So that is a worst face, right?
Yeah, because you can say P4 must be weight
Oh, okay, I see.
on this map. And on the first page, P4 also must wait until some process is finished. So we will move to the question 2. And if a memory take 200 seconds time unit, how long does the page memory reference take? So it will double it because you have one time to read the page table and plus one time to read the word in the memory. Because on the paging system, you have the page table and the memory. So you should take one time to read the page table and one time to read the memory. However, if you have a register and 55% of page table reference are can found in this register. So what is the 8? Okay, so you have 55% of time can found it in the memory. So you should first you should read the memory. Read the register, and then you should read the word in the memory. So this is the successful, and if you fail, then it will become, so you have 35% failed, then you should read the register and it will fail, and then you should read the page table, and then you should read the memory. So this is the effective memory access time. And it's this one.
But this is 420 and it's 400. What's the
What? So you just read it too. This is for the page table. You read on the page table,
Yeah.
and this is you read on the memory.
Why is there 20 spot?
Okay, so it's just combine this together, so it will equal this one.
Yeah.
Right. I just use this more.
Oh, okay.
Okay. Yeah.
Yeah.
Okay. Okay, so question 3 is that if two users use in one page table to print the same page film in the memory, and what is the disadvantage and advantage? So the user can share their code and data. However, because they share the code and data, which means they can change the other one's code. and modify it, so it will cause some safety problem. Question 4 is why the segmentation and the page sometimes can combine into one plan. So in the paging and the segmentation is that paging provide like a fixed size, and segmentation is divides the program into variable size. And paging is operation system response, but segmentation is user or the compiler defined. So in the process, it can system page is useful, and because it can combine two convenience. Because it's easy to placement, and the logic is easy to understand. And then we will move to question 5. Okay. So question 5 is that you have 5 segments, and you have base, which means the star address, and you have length. And what is the physical address for following logical address? So this is the number and like an index, and the second one is the length. So for the process 1, process 0, it length is 430. So it's which is smaller than 600. So it can place in the memory. And for example, you have a memory which is star at this one, and this length will be 600. So it will finish at the 890. So it can place the first one, because the first one is only occupied 430. And for the process 1, and process 1 is the length is 10, which is smaller than 40. So process 1 can place in the memory. And process 2 is illegal, because 500 is smaller, is bigger than 100, so it don't have enough time, enough memory to put it. And process 3, because 500 is greater than the 400, so you can put it in the memory. And process 4 is 112 is greater than 96, so you can put it on the you cannot put it on the memory. So then we will move to quickly to talk about question 6. And in this one, IBM designed memory protections, and each 2K blocks of memory have a K, and the CPU also have a K, and is store operation is only allowed if both k are equal or if 1 is 0. So, which of following memory management plan could be used successfully in this hardware? So, bare machine. So, bare machine is you execute the instruction directly to the hardware without the operation system. So bare machine is protection is not necessary, and you just set the system key into 0. And in the single user system, so in the single user system, you should set the system key to 0, and when in supervised model, then you can just store the memory. And if the multi-programming with the fixed number of process, then you should store the memory increment of 2k bits. So it can occupy each 2k blocks of memory have the k. You can fulfill these conditions. And the multi-programming with the available number of process is the same with the above. And if the paging and segmentation, so the film size must be increments of 2k, and so it can allocate the key with the pages. And the segmentation is the same. The segmentation size must be the increment of 2k bits, so it can allocate the keys with the segments. So that's all for today.